This video is about radicals and the way that we're going to use radicals in geometry. We need to be able to reduce them or simplify them, and we need to rationalize our denominators. We'll start off by what a radical is and some of the basic rules, and then we'll talk about reducing radicals by factoring out perfect squares and what it means to rationalize a denominator. I'll run through an example and then we'll summarize. A radical is anything that has a square, cube, or etc. root. Most of the time that you've used these, you've done square roots, which are the opposite of squaring something. A cube root is the opposite of cubing something, or raising it to the third power, and the cube root is this last one over here. The rules that we're going to use most often in geometry class are the rules that let us move between the factored version. We can take two radicals that are being multiplied together, combine them into one radical, or we can go vice versa. We can take one radical, break it into its factors, and break it down into two radicals. This is like saying the square root of 2 times the square root of 5 is equal to the square root of 10. This works the same way with division. We just show division as a fraction. So, for example, the square root of 30 over the square root of 2 is equal to the square root of 30 over 2, which is the square root of 15. The method I'm going to show you for reducing your radicals, so taking a radical that's fairly large and breaking it into a simpler version, we're going to factor out a perfect square. So a perfect square, first off, is any number that can be written as another number squared. So for example, it would be 4, 9, 16, 25, 36, 49, 64, 81, and 100 are the first 10 perfect squares. So we take a number like 72, and we break it down into two factors. One of them is a perfect square. So 36 times 2 equals 72. Well, since we could break that into two radicals, we can take the square root of 36 separately, which gives us 6. Same thing with 48. 48 breaks down into 16 times 3. Square root of 16 is 4, but the square root of 3 doesn't reduce. One more example, and then I'll try to give you a couple of extras. 125 is broken into 25 times 5. Square root of 25 is 5, and then this piece doesn't reduce. So one more example for you. Actually, two more. 200 can be broken down into 100, which is the perfect square, times 2. Square root of 100 times the square root of 2 becomes 10 root 2, and then that's my final answer. 90 can be broken down into 9 times 10. 9 is the perfect square. So we get 3 root 10 as our final answer there. 10 doesn't have any perfect squares that divide into it. 10 is only divisible by 5 and 2. Neither one of those is a perfect square. Rationalizing the denominator is something we do that doesn't really change the value of anything. It's just bad math grammar to have a square root in the denominator. What we do is we multiply it by a special version of 1, so a fraction over itself, and we form that fraction by taking whatever square root or whatever radical was in the denominator, dividing it by itself, multiplying, and then simplifying. And you'll always get this same pattern here. Sometimes A and B reduce, so just be careful of that. So here's an example. 2 over root 3, multiply them both, and we get 2 root 3 over 3. 5 over root 10 becomes 5 root 10 over 10. These two numbers simplify so that we get root 10 over 2. And I would multiply both by 3 root 7. This one becomes a little bit trickier. The 5 times the 3 becomes 15 root 7. And the denominator becomes 3 times 3. Root 7 times root 7 is root 49. So this becomes 15 root 7 over 9 times 7. The 15 and the 9 are going to cancel out. So we get 5 root 7 over 3 times 7, which is 21. If you need help with that one, let me know in class. I can run you through it again. Alright, I'll try to make our last example quick because I know I'm running a little bit longer on time. If we have this isosceles right triangle here and I want to find both sides A and B, side A is probably the harder one, so let's do that second. Side B is easiest because they're more congruent. So what I have here to find side A, I'm going to use the Pythagorean theorem. I knew normally this is C, but it was A in the diagram. Sorry if that's confusing to anybody. I take the square root of both sides, and now I'm going to reduce this 8. So that breaks down into the square root of 4 times the square root of 2, which reduces to 2 root 2, which is A. You should jot down in your summary, briefly describe what a radical is, what we're trying to factor out to reduce the radicals, and what is it that we're looking for that I called bad math grammar.